Hey guys, Mr. Smith here, and in this video lesson, our first lesson of our final unit, Unit 8 on combining functions, we're going to talk about adding and subtracting functions. We're going to look at what happens when you do this algebraically, when comparing the graphs of the sum or difference of two functions. It should be good. And, I'm sure everybody already has some practical experience with this idea. If you swam in a pool, the ocean, a wave pool, you've seen the effect of waves. And in a wave pool, especially, things can get really interesting. But in some spots, the waves, you might have waves just kind of like normally, and then all of a sudden you get a huge wave. Or sometimes you might get a huge kind of dip. When you have multiple waves kind of meeting each other and interfering with each other, you get all these crazy patterns. You get highs, you get lows. And that's with just two waves. When you start to consider more waves or more functions and how they interfere, how they add together, how they subtract together, the math can get pretty involved. So we're just going to keep things simple today, and we're going to look at two functions, not necessarily two waves, like two sine functions, but two functions and what happens when they meet if you were to add those two together. Just as a little visual, if you've taken physics, you in grade 11, you guys look at waves, and you might be familiar with the superposition of waves. If you haven't taken physics, it's okay. You're going to be just fine. But this idea of superposition in waves basically says that, if I have a wave, let's say I have a sinusoidal wave, and it kind of meets up with another sinusoidal wave, looks the same. Like, for example, let's say this wave is traveling this way, and this wave is traveling this way, and they meet. The superposition principle says that they kind of like combine together, and their highs get really high, and their lows get really low. Kind of eating up my space into destructive interference, but that's okay. What destructive interference says, let's say you have two similar waves, but this time those waves are shifted a little bit. Let's say there's a little bit of a phase shift going on. So they're perfectly like out of phase, where one has a high point, the other one has a low point, and vice versa. And say this guy was going this way, this guy was going this way. What would happen is we would get destructive interference. So the positives of the first wave add with the negatives of the second wave, and you would actually get no wave at all. You get like perfectly flat water. For that instant of time. So this is the idea behind waves and how waves can kind of combine. And in math, there's actually a similar principle, the superposition principle. But here's what the superposition principle says in mathematics. This definition might have a couple of terms you haven't heard before. That's okay. Oh, my dual monitor is making funny colors here. All right, the superposition principle kind of has to do with when you are adding two functions together. So the superposition principle states that the sum two functions, and you know what, we're going to do it with the sum of two functions today, but the things we do today with two functions, you can do with two or more functions. The sum of two more functions can be found by adding the y coordinates. And the fancy word for y coordinates is the ordinates of the functions at each x coordinate. And the fancy word for x coordinate is abscissa. Definitely a word you don't use every day. We just usually say y values and x values, y coordinates, x coordinates, ordinates, and abscissa. So it's actually a really simple idea. It's if I have two totally separate functions and I want to find the result of adding those two functions together, you just add their y values together at the corresponding x values. So it's really kind of It might look like a fancy definition, but it's a really simple idea in practice. And let's just do a couple of examples, looking at what happens algebraically, what happens visually. So we're going to, one, for each of these two functions, f and g, we're going to determine algebraically the function where we add these two guys together and look at what happens with the graph. Also talk about what happens with the domain and range. So for our first one, we're using f at x equals x squared, g at x equals 3. And we're looking at the combined effect of adding those two functions together. Well, shouldn't be shocking, the equation for the sum of those two functions, f of x plus g of x, is just going to be x squared, that's f of x, plus 3. That's it. And that actually that's a quadratic function. You're familiar with what it looks like. Let's dive in here. And you know what? You even know how to graph that one. I mean, the graph of this guy. Well, you know what? I'll save that for a second. But let's just compare the algebraically what happens with the values for each function. So for f of x equals x squared, the ordinates, the y values would be, for these x values of minus 2 to 2, would be 4. I almost put 1 times 1 is 2. 4, 1, 0, 1, and 4. Of course, for the constant function, g of x equals 3, the y values, the ordinates, are just all 3. And to get the values of the sum of these two functions, x squared plus 3, you add these together, 7, 4, 3, 4, and 7. Now, if we're going to graph these guys, and I'm just going to, maybe I'll use this color for that guy. It looks like green will show up okay, and I'll use this color. You can choose to do whatever you like in your own notes, but of course, we all know what the basic parabola looks like. So there's our graph of f of x. G of x is the constant function, 3. Pretty easy to draw. Pretty easy to draw. You know what? I'm using Cami right now. No reason why I can't just draw a straight line with the straight line tool. No reason for me to rough it. There we go. And our function h of x is the function x squared plus 3. But look at the graph of this guy. The graph of this guy comes from just adding the y values of each function. So let's do that visually. At negative 2, we've got 3 plus 4, 7. Positive 1, positive 3, positive 4. 0 plus 3 is 3. 1 plus 3 is 4. And 3 plus 4 is 7. And of course, we already knew what that's what the graph would look like. I mean, x squared plus 3 is a parabola that opens upwards with the same shape as the basic parabola, and its vertex is at 0, 3. So, like, you know, if you were, I'm not sure what else we would expect to happen with this guy here. The y values added together. That's what happens when you apply the superposition principle. The y values add together. We're just looking at that with some really basic functions here. What is the domain of this sum function of f and g? Well, we can see that it's a parabola. But like if we look at our base functions, the domain of f of x equals x squared is x can be any real number. The domain of g of x equals 3 is x can be any real number. So when you add those two together, you know, you're going to get for any x value in h, an x value exists for f and an x value exists for g. The domain is just going to be that shared x can be any real number. Of course, we know that that function h is just a quadratic function, so its domain would be any real number. The range After drawing it, we can see that the range is the y values, any real number, such that the y values are greater than or equal to 3. In this case, it was obvious. Maybe in the next one, it wouldn't be so obvious. Let's check this next one out. Now, our table and our graph, we're going to produce the same way. Here, our base function, or our function f, is still x squared, but this time we're going to use x for our second function g. We're looking at the sum of these two guys. That'll be the function x squared plus x. Now, right off the hop, if I just asked you, like if I asked a grade 10 student, or even you guys, sketch the graph of x squared plus x, by hand, not exactly an easy thing to do. I mean, you might be able to kind of mentally figure out by factoring where the x-intercepts are, where the y-intercept is. Finding the vertex would be generally a challenge, but we can graph functions like this by just thinking about x squared plus x in terms of one function plus another. Let's do that here. So we have our first function, x squared. The y values are the same as they were before. For g of x equals x, the x values would be just -2, -1, 0, 1, and 2. And we can actually get a table of values in a graph pretty quickly by just using the superposition idea, just adding the ordinates, adding the y values. When we add these two together, we get 2, 0, 0, 2, and 6. And let's graph those guys. Well, first, let's actually follow the same pattern from before. I'm going to just use the same color scheme. That guy for that guy, that guy for that guy, that guy for that guy. So 0, 0, -1, 1, -2, 4, 2, 4. So symmetric. Now, as I'm drawing this, we already know that the graph of h of x it's a quadratic function. It's going to be a parabola. It's just like, what are the properties of that parabola? For x, we have 2, -1, 0, 1, and 2. And I'll make sure to use my straight line tool. And that is going to be a linear function. That's our function g. This was our function f. All right, what's the graph of the sum? Now, one interesting thing here is that when you add a quadratic function together and a linear function together, you get another quadratic function. That makes a lot of sense in the algebra. Like, you'll have an x squared term, an x term, and a constant term, plus a function that has a linear term and a constant term. But graphically, it's kind of cool too. It's not necessarily evident that when you add the line values and the parabola values, it makes another parabola. But let's check it out. So for -2, writing -2 and 4, that gives us +2. 1 and -1 gives us 0. 0 and 0 gives us 0. 1 and 1 gives us 2. And 4 and 2 gives us 6. Now, I'm going to add a little bit of detail as well. We can see the symmetry here. It's clear that our vertex will be at -0.5. And so I know another point will exist if I go over at -3. I know I'm also going to be at +6 because of the symmetry. Now, I'm just going to connect the dots here. I'm going to draw my parabola through this one here. And I'm going to draw it right now, understanding I don't exactly know where the vertex is right away. This is just a rough sketch of this parabola. All right. What's the domain of this guy? Well, again, look at the base. Look at the pieces making up this the sum of two functions, x squared and x. The domain of each of those functions is x can be any real number. There are going to be no issues adding these functions together. The domain will be x can be any real number. The range we have to think about, actually. So we don't know what the range is initially. We know that the x-intercepts of this function are -1 and 0, and then it dips below that, but we don't know how low. So we can find this out. We can do that a variety of ways. We can find the zeros and use the axis of symmetry, and since we know the zeros, it's probably the best idea. You could complete the square, but let's use the axis of symmetry. The axis of symmetry, I'll just use short form for that, is at x equals, if you weren't sure how to get it, you just add the zeros divided by 2. It's at x equals -1/2. What's the value of the function at -1/2? Should be h at -1/2. -1/2 squared plus -1/2. So that would be 1/4 minus 1/2. And a half is 2/4. 1/4 minus 2/4, you get -1/4. And so the vertex of this parabola is actually at the point -1/2, -1/4. And so now we can state the range, right? Now we can state the range. The range is y values such that y is greater than or equal to -1/4. So using the superposition principle is great for, say, graphing a function that's the sum or difference of two functions, but there still might be some work going into finding the domain and range. Okay, now we did this example to illustrate these two examples to illustrate the superposition principle, kept them pretty basic. We looked at the table of values and the graph. In the following, all I want you guys to do is produce the graph. I've given you guys the graph of the functions we're adding. And then in B, since we haven't done the subtraction of two functions, I want you guys to try B as well. The superposition principle works the same way. If you're subtracting two functions, you subtract the ordinates, you subtract the y values. So if you want to pause the video and give this one a try, go for it. If you feel more comfortable following along with me, that's okay too. But yeah, this is neat. So here we're adding a linear function with a sinusoidal function. But to get the graph of this function h, no big deal. We just add the ordinates together. -6 plus 1 is -5. -4 plus 0, -2. I got to be careful here, just make sure I do it right as well. 1 plus -6, -5. -4 plus 0. Yeah, that's definitely not right. I was averaging them. -4 plus 0 is -4. -2 plus -1 is -3. 0 plus 0 is 0. 1 plus 2 is 3. 0 plus 4 is 4. And then finally, -1 plus 6 is 5. And what you get here is you actually get this cool function. It's it's not exactly like this, but it's almost like a sinusoidal function, just kind of like tilted on its head a little bit. Something like so. That would be the general shape of our function h of x. Not really concerned with what the equation of that would look like. Right now, my idea with this exercise here is to get us just used to applying the superposition principle graphically. If you haven't tried the next one, finding the difference of two functions, give it a try. Pause the video. You can unpause when you're ready. But again, you can follow along with me as well. Here we go. Negative. So we're just to be clear, we're doing f of x minus g of x. F of x is the blue parabola here. G of x is the red sinusoidal function. So we're subtracting the blue y values from the red y values. 9 subtract 3 is 6. 4 subtract 2 is 2. Here, 1 subtract 1 is 0. 0, remember we're subtracting blue from red. 0 subtract 2, -2. 1 subtract 3, also -2. 4 subtract 2 is 2. And finally, 9 subtract 1 is 8. All right. Now, as far as what this one looks like graphically, I'm actually not quite sure. I'm going to connect the dots here anyway, as best I can. There's definitely going to be a little bit of wobble here. I think what I'm going to do is I'm going to load up Desmos and see kind of what this looks like as well. I think maybe in the future I'll just say draw the points or pick functions that line up a little bit better. I don't know. It's pretty wild. Let's actually head to Desmos and see what this looks like. So the base function I used was x squared, or one of them anyway. Well, that's a little big. Squared, and the other one was a sine function with an axis of 2, a period of, what was the period? The period is 4. And what was the amplitude? Amplitude was 1. So sine, if the period is 4, the k value is 2 pi divided by 4, 0.5 times pi times x, and then plus a 2. And I'll call that, let's actually give this a try here. If I call that g of x, call that f of x, and I think that matches up with our graph. Yep. Let's graph what h of x equals f of x plus g of x is equal to. Okay. Oh, we're doing the difference. Excuse me. Okay, so pretty neat. Kind of like a skewed parabola almost. Yeah, very interesting. How did I do? You know what? My critique with mine is that I have it kind of like inflecting where it should just be more just like a parabola and not really. It should just be curving up. We'll just leave it like that. Yeah, very interesting. But what I would expect you guys to be able to do, what's the moral of this story? If I gave you guys two graphs and asked you to find the sum or difference of those two graphs, that you would be able to apply the superposition principle. Now, just before we move on from this example, alternatively, you could think of the difference of two functions. You could think of it as h of x is equal to f of x plus the negative of g of x. So for our problem here, what you could have done is you could have just drawn the negative of the red function g of x, the negative of that sine function, which not too hard to do, would just be something like so. That would be negative g of x, and then add the ordinates, the y values of that green function and the blue function f of x. If you find that less confusing, if you find that adding the coordinates together helps you out, then just do that. Or like I did, you can just subtract the coordinates. You get the same answer either way. All right. So that's kind of the meat and potatoes of the lesson today. It's the superposition principle. Maybe for some of you guys that just kind of said, yeah, I don't see what the big idea is. It just made a lot of sense. It's the superposition principle. It's adding functions. It's not complicated. You add their y values together. We're going to look at an application of the superposition principle, a business application, and it's called the profit function. Most of us have enough business, not maybe experience, but exposure to business to understand the relationship between profit, cost, and revenue. When you're manufacturing something, when you're selling something, there's always a cost to manufacturing or producing an item. There's the revenue, the money that you make by selling that item, and the difference between the money you make, the revenue, and the cost is called the profit. It's a natural example of the superposition principle. The profit function is always the difference between the cost function or the revenue function and the cost function. So we're going to look at that. The functions that we're going to be looking at here are linear in nature. So the algebra here is not going to be too crazy. We're just looking at an application of the superposition principle. So the context here is we're selling t-shirts. We have to make the t-shirts to sell. It costs money. And so here, it costs $200 no matter what. So, firing up the t-shirt printing machine, putting in the graphics for that, it's going to cost $200. After that, once the machine's up and running, it's that $200 is spent, and now it's just $5 per shirt. So every $5 for every extra shirt made. So this cost function, it depends on the number of t-shirts, which we're using as n. So the cost function, C of n. There is a fixed cost to this and a variable cost. The fixed cost is $200. The variable cost is $5 per shirt. And this is the kind of question that you guys might have even done, say in a grade 9 course. So fixed cost is $200 plus a variable cost of $5 for every shirt. So $200 plus 5n. And we just explained where each of those terms come from. That's the cost. And for the revenue, we are selling the t-shirts for $8 each. So the revenue function will also be linear. It's pretty straightforward. How much money do we make? What's our revenue? Well, it's simply $8 for every t-shirt that we sell. And there's our cost function, and there is our revenue function. Now, we're going to make a graph of these two guys. I believe I've picked a scale where we could rough this out. And what we want to have a look at is where they intersect. Again, this is now tying into some grade 9 and grade 10 stuff, things you may have already done before. We're just looking at them under the lens of the superposition principle. No big deal. Okay, so what's our cost function? Our cost function starts at 200, and our cost is $5 per shirt. So 10 shirts, that's $50. 20 shirts is $100. I think that makes a nice, easy point there. And so I'll just make that my kind of guide for drawing this linear function. And I think I'll just stop there. I'll use the same color. And if our point of our point of intersection may or may not be easy to read off the graph, we're going to find it using algebraic techniques from earlier grades as well. So this is the cost function, 200 plus 5n. Let's look at our revenue function. So it's 8n, so its initial value is 0. Okay, and every 10 we sell, we're making $80. And that is okay to use this scale. Every 10, we go up by 80. So 60, just be careful here. It's going up by 4 ticks every time. So 50 would be 400. Everything is looking fine. Okay, we're still not there. It's looking a little, 70 would be 560, which would be right there, but not quite on the pink, the purple graph. And so I'm just going to draw this in, the straight line tool, pick the same color, like so. This is our revenue function, 8 times n. All right. It appears they meet somewhere between 60 and 70. Not exactly sure where. We can use algebra to find the point of intersection. So we are going to do that. We are going to set the cost function to be equal to the revenue function, just applying some ideas from your grade 10 math course. So 200 plus 5n equals 8n. We can collect the n terms. 200 equals to 3n. And 200 divided by 3, well, 200 over 3 is exact, but we're talking about number of t-shirts. So that's approximately 60, I got to be careful. It's just 66.6 repeated, right? So we'll say approximately 66.7. And that would be t-shirts. Of course, what's the corresponding value of R or C? I'll just say find R equals C, because at this point of intersection, the revenue and cost would be the same. I'll just choose the revenue function. Looks a bit easier to work with. 200 divided by 3. So that's 8 times 200 over 3, which is 1600 over 3, which I think is 500. Oh boy, I'm going to get myself into trouble here. I'm just going to use my calculator. 533, I thought so. About 533.33. I'll put approximately. That's about how much revenue you'd bring in. Of course, that's how much it would cost to make as well. So what does this mean? It means around 67 t-shirts, we have the cost of the t-shirts matching the revenue of the t-shirts, and basically we don't make any money, we don't lose any money. It's called the break-even point. Again, you may have talked about things like break-even points when you did linear relations in grade 9, when you solve a linear system like we did here in grade 10. Again, we're just looking at this in the context of the superposition principle. Let's just jot down what this means. This means that a student council sells, we'll just say about 67 t-shirts. And the revenue and cost will be about equal. About $533. This is known as the break-even points. So in terms of the superposition principle, I want you guys to be able to create an equation, create a graph of the sum or difference of two functions. But also, you guys should be comfortable using setting up a profit function like we'll do in a second, and finding a break-even point. That is an expectation. I'd like you guys to know in this context how to find a break-even point. Let's go into part B. Part B asked us to find the profit function. So remember that I'll just jot this down actually. Profit is the difference between revenue and expenses, i.e. the cost. What does that mean? Well, our profit function is going to equal our revenue function minus the cost function. This is the difference of two functions. It's the superposition principle. We already have expressions for those two functions. Revenue function is 8x. The cost function was, I'll put the 200 first. 200 plus 5x. 8x minus 5x, 3x, and then minus 200. Now this profit function makes a lot of, I'm using x. I should be using n. please forgive me. I'm just going to clear all this out and just redo that. Not a huge deal, but we are using n for number of t-shirts, so I don't want to change that. 8n minus 200 plus 5n, which gives us, again, 3n minus 200. All right, again, this makes a ton of sense. Let's think about this. What if we don't make any t-shirts at all? What if we don't produce any? We're not taking in any money. We've paid $200 to set up the machine, so we've lost $200. So our initial value here for profit, the lowest we can lose $200. And the 3N makes a lot of sense too, because it costs $8 or it costs $5 to make a t-shirt. We sell it for $8. For every t-shirt, we are making $3 extra. So this profit function makes a lot of sense. So for part C, we're talking about when are we making money, when are we losing money? Well, it's all about that break-even point, right? So more or less, we make. We're asking. And we want to add. I think we actually want to add this profit function too. Let's do this the best we can. What's the best color here to use? Let's use green. Now you can just graph the function to a 3n minus 200, or you could also just add the values we have on our graph. For example, for the x or the n coordinate of 0, the y coordinate, or p, is going to be 0 plus 200. It will be the difference. It would be 0 minus 200, so minus 200. At these x values of the n values of 20, I have the values. We have 160 minus 300. That's negative 140. For an x value of 40, we have 320 minus 400. So that's negative 80. At 60, we have 480 minus 500. That's negative 20. And do we have any other values on the graph? We don't exactly have any other values on the graph. So let's add more so again, that's one method of graphing the sum or difference, just subtracting values in this case. But let's actually let's actually think about this function. So it's minus 200 for its initial value. And then our slope is 3. So, every 10, we're going up 30. Every 20, we're going up 60. So that's actually an easy rule to use. Over 20 more, we're going to go up 60 more. I can do one more over here and here. I'll get my straight line tool. Use my mouse for that. There we go. And this is our profit function. All right, and you can see, when does our profit equal 0? When do we break even? Well, it's part way between 60 and 70. We've actually found out when that is. So to answer part C, when do we make money? I think I can type this in. Student council loses money if the profit is less than 0. Which means our function P at n is less than 0. And we've already seen this occurs. This occurs when they sell less than 67 t-shirts. They make money if the profit is more than 0. Profit function is greater than 0. Of course, visually, this means it's above the horizontal axis. Okay. Now, one last thing we'll do with this problem, and again, like this is a problem I swear many of you guys could have completed in your grade 9 math course. For sure, you did questions like this in your grade 10 math course. But again, we're just looking at things in terms of the superposition principle, so the sum and difference of functions. One last thing we'll do is talk about the domain and range for each of these, because often real life can restrict the domain and range. Now we can see these are linear functions, so the domain and range won't be too complicated. However, there is a practical restriction here. We can sell no t-shirts or one t-shirt or three, etc., etc. But we can't sell like negative t-shirts. So for our cost function, so let's chat about that. What do I mean by that? For our cost function, I don't want green. Which was 200 plus 5n. We understand it's a linear function and that nothing mathematically really breaks down when you plug it in. You can plug in negatives or whatever you want. But practically speaking, we can only plug in certain values. We can only have integer values. Like we can only sell a whole number of t-shirts and they have to be non-negative. So we would write that this way. The practical domain, what values of n can we have? They have to be integers. So we use z for integers with looks like a 2. We use a z with like a kind of double line in the middle. I was always bad drawing those in university. And here we have to have non-negative values. N can be greater than or equal to 0. For the practical range, remember the cost was fixed $200 and then $5 for every t-shirt. So at the very least, you're paying $200. So the cost will also be an integer, and the lowest the cost can be, terrible too. We'll get that right. The lowest it can be is $200. The cost is going to be greater than or equal to $200. We'll do the same thing for the revenue function. The revenue function was 8n. Okay, so again, you cannot sell a negative amount of t-shirts. I'm going to get good practice drawing these z's. So n is greater than or equal to 0. What are our possible values, our range for revenues? Well, if you sell no t-shirts, you make no dollars. Like that's the minimum. Revenue is the money you take in. You can't take in negative money. You can take in nothing, or you can take in some money. So the range for the revenue, integer, the range will be greater than or equal to 0. And finally, for the profit function, which we found out was 3n minus 200. Again, practical domain. It's the shared domain, right? Like profit is the difference between revenue and cost. And to get a value for the profit function, you need a value for the revenue function and the constant function. If the domain of those guys is n is greater than or equal to 0, the domain of its difference function is the same thing. And finally, the practical range, we talked about it. The absolute lowest the profit can be is negative 200, losing $200. The profit greater than or equal to negative $200. All right. So what have we done today? We started off our new unit on combining functions by looking at adding or subtracting two functions. You can do with more. Today we dialed in on just doing with two functions. We talked about the superposition principle, which states that you can just get the sum of two functions by adding the y values at each point. So pretty straightforward. And we did an example, and also we looked at the profit function, that we can apply the superposition principle to the difference of two functions too. And what we have been talking about throughout, illustrated in this final, is that just like the profit function, it's not defined if revenue is not defined or cost is not defined. The domain of the sum or difference function is the domain common to the component functions, the intersection of those, if you will. All right. In our next lesson, we're going to talk about the product or the quotient of two functions. Should be exciting. In the meantime, got some suggested practice for you guys. As usual, if you need anything, please reach out. Be glad to give you guys a hand. Hope you guys enjoyed that lesson. I enjoyed giving it. Take care, guys. Stay well, and we'll see you soon.